This is for MET 213 for the dynamics presentation video. In this we're going to do two different experiments, and in the first portion we're going to show how pulleys, theoretical versus actual, and the tension in the ropes. And here's the first one with the pulley arrangement like this, and the second one with just one pulley, and we're going to see how the tension is different compared to what it should be. The second one is we're going to drop a mass and show the actual versus theoretical acceleration inside of in the pulley, and well, not the pulley but in the spring scale. So here's the first one. In our first experiment we have a hanger that weighs 100 grams with another mass that weighs 100, so a total of 200 grams. We have one pulley and a spring scale. We're going to pull the pulley down to the point just before the mass will move, and we're going to read off the spring scale what the tension in the cable should be. So when you pull it down with the 200 grams, you get roughly just to the point of 210 grams before the mass moves, and we're going to show you the math of what the tension in the cable is now. For the setup we just showed you, we had our one pulley, our mass, and our spring scale. Here's our free body diagram. We had our mass times gravity, which is the weight pulling down, and the tension going up. In theory, our tension in the rope should be equal to mass times gravity, which is 200 grams. We converted that to 0.2 kilograms. Our 0.2 times 9.81 meters per second squared. The tension gives you 1.96 newtons. In theory, that's what it should be. When we did the experiment right before this, the tension read off our spring scale was 210 grams. When you convert the 210 grams over to newtons, you get 2.06 newtons, which is larger than what the theory is. And we can conclude that whenever you examine tension in a pulley in real life applications, you cannot neglect the mass of the cable and the friction that is also caused by the cable and the pulley together, and that is how come you get a larger 2.06 newtons of tension compared to 1.96 newtons. And next we're going to examine with a different pulley setup. This is the second pulley setup. In this one we've got two pulleys and a mass of 300 grams hanging down, and there's the spring scale, and we're going to measure what the tension is inside the rope. With our spring scale, we're going to pull it to the point of just where the mass starts to move. And when you pull it up just to where it moves, it goes to 400 grams. And this, you can see that we have two pulleys and the tension's going to be constant in the rope, even though there is two pulleys, because this length is always going to be, whether it's moving up or down, it's going to be constant. And we're going to show you the math of that 400 grams of what the tension was. Here's the math for that portion. There's the free body diagram, and we had our 300 grams, which was now 0.3 kilograms. And to show the tension in the rope is 2.94 newtons for the theoretical, and then for experimental we measured off the spring scale 0.4 kilograms, which then is 3.92 newtons. It's larger in this portion due to the fact that the two pulleys, you have to overcome the friction, and not only one but the second one, which means that it's going to be even greater. And we didn't neglect the mass of the rope, which there was more rope, so probably more mass. And that's that. Okay. This is the second portion of the project. In this, we've got the spring scale attached to the mass here, and we're going to drop it, and we're going to use the ruler here to get the time or the distance, and we're going to record it in slow-mo to get time to calculate acceleration of it, compare it to what it should be theoretically. And so here's what we're going to do in actual live video, but we're going to do it in slow-mo to prove, and we're going to attach it so that we can get actual times off of it. And the spring scale oscillates, and so we're going to take 2 points off of it, and the video will be attached of the math also. This is for the mass of 200 grams that we just dropped. So we took 2 points off the ruler here, and we chose 2 points, did it in slow-mo, so theoretically whenever you do it, it should just be 9.81 meters per second squared, but we're going to show that it's different because down here we did the math, and we took the distances that were on the ruler of 0.1 meters and 0.07 meters, and in slow-mo we took the frame rate and the time it took to get from the 1 to 0, and it was 0.08 seconds. So you get the velocity at what it's dropping at is 0.5 meters per second. So then you're able to do the acceleration, and at the point 0 we said it's 0, the velocity is, so then you're able to do 0.5 divided by 0.08, gives you that the acceleration of the mass is 6.25 meters per second squared, which isn't quite 9.81 meters per second, because as you saw in the video, it still wants to go, it's still going down, so it hasn't quite reached terminal velocity, so it hasn't quite reached its full acceleration because it's still accelerating downward. So then next we're going to show the math for another mass that we dropped. We did a similar experiment, but this time instead of dropping 200 grams, we dropped 100 grams to see the acceleration of the mass, theoretical versus the experimental. Again, the theoretical should be 9.81 meters per second squared, but in the experimental, we did the time off the ruler, or the distance off the ruler, and off the slow-mo frame rate, we got the time. This time it was 0.1 seconds, and we were able to find the acceleration is 5 meters per second squared compared to 9.81 meters per second squared. Again, it's different because the mass is less, and it's still wanting to accelerate downward whenever it's being dropped, but it rebounds back up, so that's what the difference is.